So what is the law of conservation of energy? It says this: energy is neither created nor destroyed. We can't make it from nothing, and we can't destroy it. We can only transform it from one type to another. What this means is, if we're looking at a closed system, and what I mean by a closed system is, it's not plugged in to an outlet, you're not getting electrical energy in. Or you're not adding gasoline to the system. It's a closed system. The amount of energy you start with and the amount of energy you finish with will be the same. There's a poetic way to say it. After the Big Bang, the amount of energy in the universe hasn't changed. It's remained constant. We can move it around. There are pockets of energy. We call them stars. Brian, I'm a little concerned because I keep seeing you look down. If it's your phone, put it away. Thank you. Okay. There are stars and galaxies are pockets of energy, but the amount of energy hasn't changed. What you start with is what you finish with. Here's a really good example. It says this: both the KE, what's KE and abbreviate for? And the PE, potential energy, of a block freely sliding down a ramp are shown only at the bottom position. Now, we're going to assume this ramp is made out of ice, and so we're not losing any energy. Tyler, at the bottom, how much potential energy do you have? How much kinetic energy do you have? How much total energy do you have? How much total energy will you have anywhere else? Same answer. So, how much potential energy must I have at the top? As it starts to slide down, it loses potential energy. Why does it lose potential energy? But what's getting smaller? H is getting smaller. But that energy has to go somewhere. It can't just vanish. And so, Brian, are you looking at your phone again? I hope not. Okay, calculator. Thank you. Sorry, I was going to really freak out if you were. So then here's my question, Tyler. How much kinetic energy must there be? Yep. I think you were right. That's what I think you're right. I think the first answer you said, I think was right. I just couldn't hear. Yeah. But here's what I heard. So say it loud and proud. You're right. Good. Now, what does that mean? It's sped up. Ooh. How much potential energy is there if I have 50 joules of kinetic? How much potential is there? Good. Now, you all know that when you drop something in free fall, it will speed up because there's a force acting on it. There's another explanation or another way to think about it. The other reason it's speeding up is it's losing potential energy, and that energy has to go somewhere. It's going to go into kinetic. It's got to go somewhere because of the law of conservation of energy. It has to stay the same. The total energy has to stay the same. In English, the law of conservation of energy, and Gerard, you are correct, I'm going to abbreviate it as C of E, says the amount of energy a closed system has never changes. As an equation, stored energy initial plus motion energy initial equals stored energy final plus motion energy final. But folks, what's my abbrev for stored energy? PE. What's my abbrev for motion energy? PE initial plus KE initial equals PE final plus KE final. Did I give you that on your formula sheet? Yeah. Did I put PE first or KE first? It doesn't matter because you're adding as long as it's initial plus initial equals final plus final. So when I'm doing this from memory, sometimes I'll do KE first, initial. Sometimes I'll do PE, initial first. But it's initial plus initial equals final plus final. What you start with is what you... Yes, that's the law of conservation of energy. We can be a bit more accurate. If we wanted to bring in friction here, Tyler, then this would start out at 75, but after a while, these wouldn't add to 75 because you'd be losing some energy to friction. But the amount of energy you lose to friction, heat, plus the total energy would still add to 75. So I wrote here, if I want to be more accurate, we could say this. KE initial plus P E initial equals KE final plus PE final plus heat. Oh yeah, you know what? I started with KE this time. Initial plus initial equals final plus heat. In other words, if the numbers don't match, it means you lost some energy to heat. Tony, a really good example of this is a half pipe in a skating arena. Sorry, a perfect half pipe where we're not losing anything to friction. Put your pencils down, look up. Okay, first I'm going to turn friction off. And what I've got here is a graph. What kind of energy did I just give this skateboarder by lifting him or her up?
Gravitational.
Okay, see it in blue? And the total energy is the yellow line. As I let this skater go, what do you notice? Is the total energy changing? But what's happening is potential is turning into kinetic, back to potential, back to kinetic. Where is my kinetic energy going to be at its maximum? Why? Because my potential energy there, well, what's H as a number exactly if I'm on the ground? What's my potential energy as a number exactly? It's all kinetic. This is also the physics of on a swing set. Swing set, very, very similar as well. At the bottom, you've gone down to your lowest potential energy. You're at your maximum speed. How fast are you traveling at the top of the swing for a split second? So, how much kinetic energy should this skateboarder have here? 0. Now, this is not what happens in real life. I've turned friction off. In real life, you have to keep adding energy from your own body to do this because you're losing energy to friction from the wheels, but also air resistance. You're running into air molecules and you're giving them energy. So I'm going to turn friction on. There you go. Which one do you see is slowly getting bigger? Thermal, another word for, starts with letter H, heat. Is the total energy changing? No. But this is basically the curse of our universe. Anytime we're doing any kind of useful work, we're losing a certain amount to heat, and it's energy that we typically can't get back. So eventually, unless you add more energy to the system, you end up with that. That's the fate of the universe. In fact, we can calculate it. We know approximately how much energy there is in the universe based on the stars and the galaxies, roughly. And so it'll take a few trillion years, but eventually all of the heat from all of the stars and galaxies will be spread out evenly all across the universe. The average temperature of the universe will be about 2 degrees Kelvin, about 2 degrees above absolute zero, the end. There won't be any way to get that energy back. The end. There's a famous poem by Robert Frost where he wonders, will our world end in ice or in fire? And what he means is, will we kill ourselves off in ice because we don't care, or in fire because we care too much, because we have a war? No, actually, spoiler alert, the universe will end in ice. That's depressing. Sorry. Oh, it says, show marble energy transfer device. So you might see behind me, let me pause. So, basketball, great example of conservation of energy. At the top, all gravitational potential energy, all MGH. Halfway down, it's half MGH and half a half mv squared. At the bottom, it's all a half mv squared. Pile drivers are also a very good example. In a pile driver, you give it gravitational potential energy, and then when you let it go, when it hits the ground, it's all kinetic energy. Let's do one together. Example 1. A projectile is launched straight up into the air. If its initial velocity was 75 meters per second, how high does it go? And then it says, use energy and ignore air friction. Don't write this down, look up. If it didn't say use energy, Gibson, I would have said, well, okay, D equals question mark. A is negative 9.8. VI is 75. I would use kinematics. In fact, I think I could probably solve it with VF squared equals VI squared plus 2AD. I'm pretty sure. And get the D by itself. but it said to use energy. And I'm doing that for a reason, not for part A, but for part B. So let's try it with part A. What is the law of conservation of energy? It says kinetic initial plus potential initial equals kinetic final plus potential final. Then before I go further, I always ask, are any of these zero? Now let's talk about when that's the case. Potential energy is going to be zero when? When will kinetic energy equal zero? Fancy word, starts with the letter R, at. Okay, and so when V equals zero. So here we go. Gibson, let's look at the potential energies first, the PEs. Are we ever on the ground? And if so, initial or final? I think we can say that, yes? Yeah, of course. Everyone knows PEI isn't a real province, right? They call themselves a premier. They're a mayor at best, right? PEI, Prince of Rhode Island? Joke there? Okay. What about kinetic? Is that ever zero? Are we ever at rest? In fact, you know what? This is similar to the skate park. The skate park had the curvy thing because it was a scalar. Who cared? But yeah, it's the same kind of physics here. I can say this. Okay. What's my equation, Gibson, for kinetic energy? No, not just equal. Just read me the equation. No. What's my equation for KE? Something squared. That's all I want. You don't just say kinetic energy equals. I want to replace this KEI with a half MVI squared. Why VI? Because it's KEI. Equals. Now you know where we're going. What am I going to replace the potential energy with? And what am I going to replace the potential energy final with? MGH? Yes. Before I go further to my calculator, I can save myself a tiny bit more time. Is there an M in the first term? Is there an M in the second term? Is there an M in everything? Then you know what? M's cancel out. What am I trying to find? H. How would I get the H by itself? How will I move the G over? Okay, so it's going to look like this. I'm going to put the H final here. I guess the VI squared stays on top. There's a 2 on the bottom and a G. Everyone look up for a second. Tony, you too. Tyler, you too. Keep looking up. Don't write this down. Keep looking up. Don't write this down. There's the 1/2. See the 1/2 V squared? I just didn't bother writing the 1. So if you're wondering why there's a 2 on the bottom, well, there it is. The G ends up on the bottom because it's being divided. And there's my V squared. Okay. Now you can write this down. Let's crunch it. What was VI? 75? Don't forget the squared. All over 2 times, not negative 9.8. We're in Scalarville. 9.8. I get 287? Okay. Which we could also have figured out by using VF squared equals VI squared plus 2AD. We would have to do a vector-based approach, but it still would have worked. Okay. What we couldn't do with VF squared equals VI squared plus 2AD is answer part B. Now we can be a little more accurate. Suppose we did this experiment, but the projectile, instead of reaching 287 meters of height, only reached 125 meters of height. What happened? We must have lost some energy to air resistance or air friction. Now, air what? Starts with letter F. Anytime they're talking about friction energy, like that, they mean heat. So I'm going to repeat this, but this time I'm going to include heat. It's going to be KE initial plus initial equals final plus final, but this time plus heat. I'll do heat in red, so ooh, fire, heat. Cole, are any of these zero? Well, are we ever on the ground? So the good news is no or yes. One of those answers is correct. It is a binary state. Are we ever on the ground? Yes or no? Where? At the start or at the end? So is that going to be initial or final? So what can I cross out? VF? So you said? I don't see a V here anywhere. No. Okay, so you ready? Did you write that down in black? Okay. If we're on the ground, look up. If we're on the ground, what can we cross out? Initial or final? Are we starting on the ground or ending on the ground? So what can I cross out? Are we starting on the ground or ending on the ground? Yes! You were way overcomplicating that, my friend. Okay? Starting on the ground. Now, let's look at the speeds. Are we ever at rest? I think we are. Are we at rest at the beginning or at the top? If we were at rest at the beginning, will we go anywhere? Yeah, remember, this is very similar to the skate park. I think at the very, very top. Okay? So, what can I cross out? Yep. Same as up here. Right? Same idea. We said you're ending up at rest. Now, sometimes you'll start at rest, then you can cross out the kinetic energy initial. Sometimes you'll end up at rest. You can cross out kinetic energy final. Sometimes you can't cross out anything, but we always look because it's nice if that works. Let's keep going. What's our equation for kinetic energy, Cole, my friend? So for KEI, I guess I can write 1/2 mVI squared, and then the equal sign drops down. What can I write for PE? So what can I write for PE final? MGH final. And then the plus heat drops down like a domino. You all right with that? Good. Is there an M in that term, my friend? Is there an M in that term? Is there an M in that term? Yes. See it? Is there an M in that term? Is there an M in heat? Be obvious. Do you see an M sitting there? So can I cross out the M's this time? No. Okay? So here I could cross out the M's because there was an M in everything. Is there an M in everything here, Cole, my friend? So can I cross out the M's here? No. What are we trying to find? How much work did air friction do? That's heat. The work done by friction is heat. Let's get the heat by itself. How will I move the MGH over? This will drop down like a domino. In fact, on the next line, I would drop down my 1/2 mV initial squared. How will I move the MGH over? Yep. I had somebody this morning say, isn't it swappy dance? No, if that was negative, I would swappy dance, but there's no negative there. So it's going to be subtract the MGH final. And then, Cole, technically that equals heat, but do you mind? Can I put the heat equals on this side where we're used to seeing the thing by itself? Is that okay? Have we got the heat by itself? Let's crunch the numbers. It's going to be 0.5. Cole, I've scrolled down. What was the mass? And then VI, was it 75, folks? Don't forget the squared. Minus 12 times 9.8 times... Oh, what's my final height here, Cole? Read carefully. No, read carefully. Read part B.
Oh, okay.
No, read part B. You got it. What? Yeah, don't use my... They're saying it didn't go to 287. It only went to 125. If you plugged in 287, by the way, you'd get zero heat, and you would... Because that would be saying there was no heat. What do you get? Write it down. Type it in. Here we go. You okay with this, kiddo? You're overcomplicating it, I think, trying to read way too much into it. $19,050? Anybody else? It's Gerard. I don't trust him. 19050? 190. Okay. Cool. Ooh, part C. Tony, what's part C you want me to find? Now, I might be tempted to say this is a job for a free body diagram. I don't think it is. And the reason is, what did we just find in part B? I got to be fussy. First of all, we did not find air resistance because air resistance is a force. This answer is not in newtons, so it's not air resistance. What did we find? Heat, which is also, Gerard, you said the magic word, the work done by what? So you ready? This here is also the work done by friction. That's another way to think of heat. It's the work done by friction. And so, how do I find work, Tony, my friend? How do I find the work done by friction? I think it's going to be force of friction times distance. Yes? Get the force of, it wants me to find the force of air friction. Okay, get that by itself. How would I do that, Tony, my friend? The average force of friction is going to be the work done by friction, if you know it, which Cole, you just helped us figure out, divided by the distance. The work done by friction is 19,050. Cole, which distance? Yes. And the distance and the air friction are in the same direction. Technically, you could argue this should be a negative number. This is a heat loss. You know what? I'm just going to find the magnitude. I don't care. Tony, what'd you get? 152.4? And that's newtons. Why did I say average force of friction? Remember, the force of friction changes if we speed up or slow down, which we would be doing here, and we don't have the ability to handle that. Mr. Dewick has a very cool demonstration of conservation of energy. He does. So the law of conservation of energy is all around us. When do I use this? Well, first of all, when do I use this? When my relatives ask me a question? Marvel movies are a classic example. So let's pick a Marvel superhero like the Hulk. Even if somehow gamma rays could do that to you, when the Hulk is, for example, throwing a car, he's giving that car potential and kinetic energy. That energy's got to come from somewhere. Even if you could create something like the Hulk, he'd have to be eating 24/7 just to get the energy to move. He would not have time to do any type of superheroing along those lines. Most of what you see in the Marvel movies, the basic rule it violates is the law of conservation of energy. In any of the superhero movies, you would say, okay, can't be doing that. In physics, when do I use it? So I've always tried to teach you when do you use something. You use conservation of momentum when there's a collision or an explosion. When is this job for a good free body diagram? We see a mu more than one force. So when do I use the law of conservation of energy? When there's a change in speed and a change in height. And especially when there is a yucky, curvy path. Like a roller coaster. Conservation of energy is great for analyzing roller coasters. Oh, also ski hills. I like example 2. Example 2 is a nice question. At location Z, a 72-kilogram skier is traveling at 18 meters per second. How high up the next slope can the skier reach? Ignore friction, so we'll ignore heat, and let's assume the skier just stays in a tucked position, isn't using their poles, they're not adding energy to the system. Okay. I think the first thing that I would probably do is put a little I right there. That's initial, and I guess final is going to be right there. This is really similar to the skate park in that all of the kinetic energy is going to turn into what type of energy, Noor? All of the kinetic energy is going to turn into what type of energy at the top? Yes. Is there a change in the height in this question? Is there a change in speed? Is there a yucky, curvy path? Conservation of energy. So the first thing you and I are going to write is K E initial plus P E initial equals K E final plus P E final. Do I need to write plus heat? No. How do I know? Because it says ignore. Okay. Are any of these zero? Let's do potential energy first. Are we ever on the ground? And if so, initial or final?
For potential?
Yeah.
Zero.
So are we ever on the ground? And if so, initial or final?
Final.
Sorry?
Final.
You're saying right here we're on the ground?
No. Initial.
What?
Initial.
What?
Initial.
Okay. Come on, PEI is not a real province. Are we ever at rest? Where? Initial or final?
Final.
And again, to try and do this with a vector-based approach, you would need to take into account every change of angle of the hill. It's doable with software, but I would not want to try and do it by hand. A scalar-based approach, much nicer. What's my equation for kinetic energy, Noor, my angel?
A half mass times velocity initial squared.
Or as we like to just say, a half mvi squared. What's my equation for potential energy final? Final. Oh, Noor, is there an M in the first term? Is there an M in the second term? Is there an M in everything? You know what happens to the M's if there's an M in everything? So even though they gave me the mass, they didn't need to. Actually, you know what this means? This explains why little kids and grown-ups can ski together. It's why they can hold hands. If the mass didn't cancel, the grown-up would have to, or the kid, would have to constantly be adjusting their speed. Now, it's not perfect because in real life there is a little bit of friction. And also in real life, a big adult has more air resistance than a little kid because your body is just larger. So the grown-up does have to do a little bit of adjusting, but not much. And it's because the M cancels. What are we trying to find? How would I get the H by itself?
Divide the other equation.
The other thing, I would have no problem giving you the same question, telling you how high they went, and asking what was their initial speed. So I would also say you can get the VI by itself as well. Let's get the height by itself. So the VI squared is going to drop down like a domino. Instead of a 1/2, I'm going to say that's like dividing by 2. And the G, when I divide, is going to end up there. You know what? That's my final height. That's how high we'll get. I've scrolled down. What was VI? 18? Don't forget the square divided by 2 times 9.8. Oh, this is almost 18 squared divided by 18. It's really 18 squared divided by 20. You're going to get an answer a little less than 18. I'm going to say in the 16s or 17s, but I can't be much more accurate than that. 16.5? That sounds good to me. Anybody else? Units? Yep. Okay. This is the law of conservation of energy. We're going to do one more. No, sorry, that's a lie. We're going to do 2 more. And then we're going to get to tomorrow, roller coasters. So we will get to roller coasters, and I'll show you how you can calculate while you're in line how fast theoretically you're going to be traveling. I like example 3. I like example 3. Example 3 is a nice question. It says, suppose it takes an average force of 245 newtons to pull the bow back a distance of 68 centimeters. Nice try. 68 centimeters. How many meters? 0.68. Ella, what's A asking me to find? Work, you say? How would I find work? Did they give me a force? Did they give me a distance? Are the force and the distance in the same direction? Woohoo! It'll be 245 times 0.68. What do you get?
166.6.
Okay. Ella, there's a part B. How much potential energy is stored in the bow? Too slow. Noor, how much potential energy is stored in the bow? Too slow. Clover, how much potential energy is stored in the bow? Darn right, 166.6 joules, because I've just done work. Remember, potential energy isn't always mgh. That would be if we lifted it. But look at the picture. Did we lift the arrow? No. We did force times distance. Okay? What I really like is C. If the arrow has a mass of 42 grams... Nice try, Duick. How do I go from grams to divide by 1,000, I think? So 0.042 kilograms. How fast will it leave the bow? Okay. In this question, there isn't a change in height. There isn't a change in speed. There isn't yucky, curvy path. But the way I know it's conservation of energy is because what's really happening is stored potential is getting turned into, yeah. And so what I'm going to write down my conservation of energy equation. Initial plus initial equals final plus final. Was that a phone that went off again?
That's two orders of that.
We'll get our orders. Ella, are any of these 0? Let's look at kinetic energy. Is it ever 0? You know what? Initial is while we're like this with the bow extended. How fast is the arrow traveling exactly as a number? So how much kinetic energy does it have exactly as a number? So initial kinetic is 0. What about when I let go of the string? What happens to all of the potential energy? PE final is going to be 0. No more stored energy in the bow. Okay? Look up, don't write this down. Have I said I like this question? I like this question. Good. Because here's the one that drives me crazy. I give this question, look up, and I see kids go like this. Oh, potential energy, that must be MGH. Don't write that down. It's not. Oh, and then you know what they do? They say, I need a height. Well, height's meters, 0.68. Now look at this picture. That's not a height. I need a mass. Oh, he gave me the mass of the arrow. And so they claim that's how much potential energy. No. The energy was force times distance. We actually know the number. Write this down. 166.6. That equals a half m v final squared. What are we trying to find?
Velocity.
Speed, technically. How will I move the m over? Yep. How will I move this 2 on the bottom over? How will I move this 1 over? Don't care, but yeah. I'm going to times by 2. You could also change this 1/2 to a 0.5 and divide everything by 1/2. I just don't like having decimals inside of a fraction. So it's going to be this. 166.6. You said times by 2, divide by the mass. That equals VF squared. VF what? How do I get rid of a squared? Okay. So it's going to be the square root of 2 times 166.6 divided by 0.042. I have no idea what the answer is. Hoping I made up good numbers. Holy smokes, 7,900 meters per... That can't be... Oh! I forgot the square root. In a panic there for a second. 89.1? Does that seem reasonable? Yeah, I think a good arrow traveling fairly fast would go about 1 football field a second. Faster than a person could throw. Not so fast that I couldn't see it moving as a blur. It wouldn't be invisible like a bullet. I would be able to kind of see a streak. That seems ballpark right to me. My Nerf dart gun works the same way. When I pull my Nerf dart gun, that's a force times distance right there. I've stored work, I've stored energy, and then when I pull the trigger, it turns into kinetic. The only issue is I've actually worked out how much force times distance that is. The amount of energy stored in here, a lot of it must be lost along the way, because this dart should come out of my Nerf dart gun at a speed fast enough that it will leave a welt on you if it hit you. They must bleed off a lot of the energy inside my Nerf dart gun. For safety, I'm sure. Right? But otherwise, it's the same concept. We're storing energy by doing work and then transforming it into kinetic. One more, we're done. A model plane flies horizontally at 22 meters per second. Okay. Nacho, what does A want me to find? Cut your zoning out, I know. What does part A want me to find? Calculate its kinetic energy. Oh, that's KE? This is not initial or final. It just wants me to find it. It's going to be a half mv squared. It's going to be 0.5 times 2 times 22 squared. Do that one. Oh yeah, I can do that one on my head because the 0.5 and the 2 will cancel. So it's 22 squared. 22 squared is going to be 4 times 11 squared. 121 is going to be 4 times 121. 484, I think. Double check me. Yes? And that's joules. B says, the plane goes into a power dive and levels off 40.5 meters closer to the Earth. How much potential energy did it lose during the dive? Ooh. Brennan, how do I find potential energy? Sorry, I went with the wrong name because I'm tired here. Good gosh. Mr. Dewick. It's Jesse that sits there. It's Brennan that sits. You both wear baseball hats that are black. And I was looking down. I apologize. In my other blog. Jesse, how do I find potential energy? And this one is gravitational. So, okay. It's going to be 2 times 9.8 times 40.5. Jesse, what'd you get? Give me all the digits. 793.8. Is that right, folks? Anybody else? Yeah? Okay. What happened to that potential energy that, by the way, you could call that negative because it's an energy loss. If you did, I wouldn't argue with you, but I'll just remember that it's a loss. Where'd that energy go? It can't vanish. What did it get turned into? We're ignoring air resistance here, I think. No, what happens when planes dive? Turns into kinetic. This is why planes speed up when they dive. Yes, gravity's pulling on them, and you can think about it that way in terms of acceleration, but you can also think about it in terms of an energy transfer. So, part C asks, how much kinetic energy did the plane gain during the dive? Everybody, how much did it gain? You all know the answer. 793.8 joules. And so part D, we could say, what's its new kinetic energy? Kinetic energy, let's call it final, is going to be 793.8 plus 484. And you're correct. If we wanted to be more accurate, we would have to include things like air resistance, but we don't have the physics for that right now, Gerard. Good point. What are you going to get? 1,200 and something 0.8. What? Give me the digits. 177.8 joules. And what I'd really like to know is part E. Now, how fast is it traveling? I could have done this all in one step with the law of conservation of energy, because I could have said the initial is a half mv squared plus whatever, mgh, where h is 40.5, and then you have no final potential energy. Pretend the ground is where the airplane is. Anyways, we can also do it this way. A half mv squared equals 1277.8. How would I get the V by itself? Divide by M. Like that. Times by 2. Like that. Then what? And then, if you're wanting to show your work and you don't want to rewrite the whole thing, I'm fine if you show your work like I did in red. I'm good with that. And then we can crunch the numbers. It's going to be the square root of 1277.8 times 2 divided by 2. Here's what I do know. When planes dive, do they speed up or slow down? Be obvious. You're going to get an answer bigger than 22 meters per second. Otherwise, you've messed up because somehow energy has vanished. What'd you get?
35.7.
35.8? Is that right? 35.7?
I don't know.
0.746?
Yeah.
So then it'll be 35.7. If we go to 3 sig figs, you were fine to 4 sig figs, meters per second. We are going to pause here. But I have a thought puzzle for you.